In this lesson, we'll discuss our first conservation drainage practice, the practice of reduced drainage intensity, and more specifically, the practice of shallow drainage. Note that in the rest of the lessons in this module, the title header on the slides will either say drainage design practices or edge of field practices, but these are all still in the conservation drainage overview module. You're in the right place, just feel free to ignore that header. The first practice we're going to discuss is very related to the concept of conservation drainage and changing the drainage design to better meet both agronomic and environmental goals. Remember, conservation drainage is those two hands shaking of agronomic and environmental goals. This is the practice of reduced drainage intensity. As I mentioned before, drainage intensity has greatly increased over the past years. While drainage coefficient, the drainage design coefficient might be the same as we've always used, for example, maybe 3/8 inch per day or 1/2 inch per day, the drainage intensity of new drainage systems being installed has relatively increased. This is mainly because we're installing drain pipes at narrower and narrower drain spacings. That plays into drainage intensity rather than drainage coefficient. But of course, both drainage coefficient and drainage intensity play into the actual drainage rate, or the actual rate that water is able to leave the field through our drainage system. There are two components or two options that come into play with this practice of reduced drainage intensity. Reducing the depth of drain pipe placement, this is known as shallow drainage, and placing the pipes, the drain pipes, wider apart in the soil. That's known as wider drain spacing. You can see from the table that both of those drainage design modifications result in lower drainage rates. First one, increasing the spacing between your drain pipes, and then the second one, decreasing the depth of drainage. That means placing those drain pipes closer to the surface in terms of shallow drainage. Let's take each of these two individually, starting with the practice of shallow drainage. Shallow drainage generally means placing the drain pipes at about 30 to 42 inches deep in the soil rather than the more traditional 36 to 60 inches deep in the soil. And you see those illustrations on the right illustrate conventional drainage versus the bottom two are shallow drainage during different parts of the growing season. Because you need to balance drain depth, spacing, and grade, depth, spacing, and grade to achieve a given drainage rate, placing the pipes shallower in the soil or closer to the soil surface means that you also need to make them closer together to achieve the same drainage rate. So this relates to the agronomic goals. We still want to make sure to provide good drainage for crop growth and trafficability, but in this case we also want to think more about improving water quality too. So with shallow drainage, if you're placing those pipes closer to the soil surface, you have to place them closer together. This illustration does a good job of showing a deep placement and widely spaced tile drains versus a shallow drainage system where those pipes need to be spaced a little closer together. Keep in mind, however, with shallow drainage, there are still minimum depths established for the placement of drain pipes to avoid crushing. If you're dealing with a 3 to 6 inch diameter drain pipe, you don't want to put it any closer than 2 feet or 24 inches from the soil surface. You don't want it any closer than 24 inches from the surface. And if you have a slightly larger drainage diameter, 8 inch or up, you want to be at least 2.5 feet or 30 inches below the surface of the soil. That's based on the ASABE standard, the design and construction of subsurface drains for ag land in humid areas. The second option for this practice is placing the drain pipes wider apart to reduce drainage flow volume. This picture is pretty washed out, but I like that it shows one field with two different drainage spacings. It looks like they used a given drainage spacing across the entire field, and then on the right side of the field came in and split those centers, or in other words, divided the spacing by 2 by installing an additional drain pipe in the middle. It looks like the right side tended to be a wetter portion of the field, and so that makes sense that they would want their drainage a little more intensive on that side. The practice of reduced drainage intensity improves water quality by reducing the volume of drainage water leaving the field. You know, after being in this course, that a load or a loss of a nutrient is impacted by both the concentration of the nutrient in your water samples that you're collecting, as well as by the amount of water, the volume of water, or the discharge of water. You have to put concentration information along with water volume information or discharge information to calculate your nutrient loads or your nutrient losses. So in this case, with this practice of reduced drainage intensity, we're addressing the second part of that equation with reducing the water volume, or reducing the amount of annual discharge that leaves drainage systems. And that's how we improve water quality. That's how we reduce nutrient loads, because we simply have less water leaving the field. Theoretically, maintaining a wetter soil profile, which is what the practice of shallow drainage essentially does, maintaining a wetter soil profile could enhance the process of denitrification. Denitrification is an anaerobic process that happens in saturated soils or in bioreactors or wetlands that stay wet. The process of denitrification in the soil, by maintaining a wetter soil profile with the practice of shallow drainage, could reduce the nitrate concentration in the drainage water. So theoretically that makes sense. That seems like that's something that could be possible, but in terms of empirical evidence where we've actually observed shallow drainage resulting in lower nitrate concentrations, we don't typically observe that. So theoretically that should happen, but in general, the main way that the practice of reduced drainage intensity works to improve water quality is that it reduces drainage volume, not because it changes nitrate concentrations. The practice of reduced drainage intensity is not a recommended practice in the Illinois Nutrient Loss Reduction Strategy, but it is a recommended practice in the state strategies for other states in the upper Mississippi River Basin that are also heavily drained states. For example, the Iowa Nutrient Reduction Strategy recommends shallow drainage is rated at 32% in-loss reduction, or it's 32% effective for reducing in-loss. And you'll note that their science team in Iowa even reported here that shallow drainage has no impact on nitrate concentration. So that's consistent with what I told you on the last slide. This practice works by reducing the drainage volume, not by changing the concentration of nitrogen in the drainage water. While this practice isn't necessarily a recommended practice in the Illinois Nutrient Loss Reduction Strategy, a benefit of the practice of reducing the drainage intensity is that this practice is applicable, or it really works anywhere drain pipes are being installed. So this practice has wide applicability. You don't have to look for a certain slope. You don't have to have a farmer that wants to do a lot of infield management. Anywhere drain pipes are being installed, this practice of reduced drainage intensity can be done. See you next time.